Let's just jump right in. Today's explainer is all about why long horizon AI requires so much more than just a larger context window. There's this really common myth floating around the tech space right now, and it goes a little something like this. If you just give an AI a massive context window, like the ability to swallow a million tokens all at once, boom, you've automatically created a powerful long horizon AI. But a long horizon task isn't just a task with a really long answer. It's an entirely different beast. What we're actually talking about is a system that can complete a complex task over many steps for a long period of time without continuous human handholding. And getting to that level, it requires way, way more than just stretching out a language model's context window. So here is the core distinction we've got to make. On one hand, you have a large context window. That's fundamentally just about capacity, right? It's receiving and holding a giant bucket of tokens. But on the flip side, you have true long horizon capability. That is about action and persistence. A system with actual long horizon capability has to plan, act, inspect the results, correct its own mistakes, and keep pushing until the final objective is met. There's a hard line between a model that can passively accept a mountain of text and an AI that can actually maintain a goal over time. To unpack why this is so insanely difficult, we're going to break this explainer down into 4 key areas: model architecture, training data, infrastructure, and finally, error accumulation. All right, first up, model architecture.
The massive hurdle here is just the physics of scaling. When you have a short context, traditional self-attention, which is what most modern language models run on, is a pretty manageable computational load. But you crank that up to a million tokens, suddenly it becomes this massive engineering bottleneck. In standard attention, every single token might need to interact with every other token. The model is forced to process this mind-boggling web of relationships, which eats up memory and slows inference to an absolute crawl.
For the math folks out there, we are talking about roughly ON squared computational growth. To put it simply, if you double the tokens, you're not doubling the workload, you're quadrupling it. By the time you hit a million tokens, the pressure on the GPUs is so intense, you could probably fry an egg on the server racks. Even if the text technically fits inside the system's memory, actually crunching those numbers demands a staggering amount of compute. Because that workload is so crushing, researchers are aggressively hunting for alternative architectures. They're testing out things like selective attention, compressed representations, recurrence, and specialized memory mechanisms. The whole goal is to drop the cost of handling long sequences while still letting the model spot important connections across the text. But here's the catch. Fixing the plumbing to reduce compute costs doesn't magically make the model a genius at reasoning. Which brings us right into part 2, training data. We absolutely have to separate what a system can technically hold from what it can actually do. An inference server might be totally fine accepting a million tokens without crashing, sure, but that doesn't mean the model has actually learned how to reason reliably across a million tokens. If the AI wasn't trained on complex, structurally demanding examples of that length, then operating at that scale is totally outside its wheelhouse. It's what we call an out-of-distribution problem. You're basically asking the model to perform in an environment it never saw during training. To really grasp that out-of-distribution gap, we need to anchor exactly how huge a million tokens is. It's enormous. We are talking about the entire Harry Potter series 5 times over, or a completely self-contained massive software repository. So trying to create high-quality training examples at that scale, it's incredibly tough, because you need data that actually requires real long-horizon reasoning, not just an endlessly long document. Useful training data can't just be long for the sake of being long. If the AI can just skim the final paragraph to get the right answer, it literally doesn't need to understand the first 999,000 tokens at all. Really high-quality data has to force the model to connect distant dots, preserve tricky dependencies, and remember early context over massive spans of text. It has to teach the model how to ignore irrelevant noise, and most importantly, how to maintain a stable goal across many steps. Finding naturally occurring data that demands that level of complex reasoning is a huge headache. Okay, moving on to part 3, infrastructure. Doing this stuff puts a crushing load on the entire hardware and software stack. Just looking at inference alone, actually generating the response, the system has to store and process a massive context. That requires ridiculous amounts of GPU memory and incredible communication bandwidth. We're talking highly optimized memory management, specialized kernels, and flawless hardware scheduling just to keep the servers from locking up. Plus, if the model needs to spit out an extremely long output, the infrastructure has to support that generation for a really long time without just timing out. And the demands during training, oh man, they are way, way more extreme. You're juggling forward and backward passes, optimizer states, gradients, all while repeatedly chewing through these gargantuan sequences. This system has to handle failures absolutely flawlessly. A single hardware blip shouldn't nuke hours of expensive compute. Literally nothing is worse than an AI having to restart a week-long task because of a server hiccup. You absolutely need robust checkpointing and a training stack that won't create bottlenecks.
So the big takeaway here is that architecture, training data, and infrastructure, they are a package deal. A sleek architecture cuts costs, but you still need the right training data to teach the model how to use it. Better training data improves the reasoning, but the infrastructure actually has to be able to physically handle the sequence length. If you have beefy infrastructure that can run 1,000,000 tokens, but you have weak architecture and bad training data, the model is just going to process a mountain of information really, really badly. They all have to level up together.
And that brings us to our fourth and final section, the ultimate operational boss fight: error accumulation. See, when an AI operates over a long horizon, it isn't just reading a long document. It's moving through time. It has to plan, act, inspect the results, correct itself, continue, and finally complete the job. This completely transforms the problem from simple sequence processing into full-blown complex system control. The model actually has to manage its own uncertainty. It has to know when to keep pushing and when to stop. Which leads us to this wild mathematical trap. Think about this for a second. What happens across thousands of steps if a system has a 99% probability of getting each individual step right? I mean, on the surface, 99% accuracy sounds incredible, right? But across a really long chain of dependent actions, that overall success rate plummets. Small errors accumulate. If the model makes one tiny mistake early on, the state of the task changes. That means later steps are built on total garbage. The AI might just confidently march forward, completely oblivious to the fact that it's drifting further and further away from the actual goal. Because of that inevitable drift, having true long horizon capability absolutely demands robust error recovery. The AI has to realize, whoops, I messed up. It needs to inspect its intermediate work, preserve enough of its own history to figure out what went wrong, and then make a huge decision. Does it tweak the last action? Does it roll back to a previous checkpoint? Or does it scrap the plan entirely? It has to constantly reallocate its limited brain power to keep its eye on the prize, even as the environment shifts around it. So, having a massive context window, that shouldn't ever be confused with solving long horizon reasoning. Capacity is just one piece of the puzzle. The real goal is building a system that can stay organized while the amount of info, the time it takes, and the chances of failing all shoot up at the same time. The real breakthrough isn't just a model that can passively accept 1,000,000 tokens. It's a system that can use those tokens, act across time, recover from its own mess-ups, and get the job done without losing the plot. Thanks for hanging out for this explainer. I want to leave you with this. What do you think will be the absolute hardest barrier to overcome on the path to true long horizon AI? Let that sink in, and I'll catch you next time.